Welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. In the previous section, we have discussed spike timing-dependent models of plasticity. Even earlier, in section 4, we have discussed rate-based models of long-term plasticity. Now the question arises, are these really two completely independent classes of model, or are these two types of models related? So let's look again at the STDP model. We look at a synapse from a presynaptic neuron J to a postsynaptic neuron I, and this synapse has a weight Wij from J to I, and this weight will change by an amount delta Wij, which depends on the timing difference, TIF, that's the postsynaptic spike, minus TJF prime, that's one of the presynaptic spikes. So if we take a postsynaptic spike, then we can center this function at the postsynaptic spike time, and I have here the part pre before post, and then I have a part post before pre, and this function is this STDP window or learning window TIF, TJF prime, the window W. So this is spike-based plasticity. Now let's also look back at rate-based models. In rate-based models, we also looked at the weight change of this connection, but we described it with rates: presynaptic rate, postsynaptic rate, joint pre- and postsynaptic rate. Now what's the rate again? The rate is a spike count in a short time window, t, and so this is, in this case, I would have 4 spikes. So I would have 4 spikes in this window t, and that's a definition of the rate. So the rate, if you want, is a temporal average over spikes or an expectation to find a spike. So the question I would like to ask is whether I can relate the STDP model to a rate-based model. Is this possible? And I will use 3 different approaches. I will start with an intuitive approach, then I will present a more mathematical approach based on Poisson neurons, and finally I will look at a more realistic model of a neuron which really uses excitatory postsynaptic potentials. So let's start with the intuitive approach. So here again, my window of STDP, or window of learning, plasticity window, and I would like to center this window at the timing of the postsynaptic spike. So let's center the window here, and then I have a part on this side which is pre before post. TJF is smaller than TIF. This gives a positive change, and the part here, post before pre. Now I also have presynaptic spikes. And now it could be that this presynaptic spike here arrives just before the postsynaptic spike that we had here. On the other hand, the presynaptic neuron could also emit a spike here. And now you see sometimes a spike arrives here and sometimes a spike arrives there. So it's clear that we don't really know exactly when these spikes arise, and if we say the spikes just arrive stochastically, then on average they might fall at any arbitrary position inside this window. To illustrate this, let's look at the next spike, and again I would have a window centered around the next spike, and there might be other spikes, and this time the spikes falls here, and maybe there's 2 other spikes falling here and there. So you see intuitively that over many different spikes on the presynaptic side and many postsynaptic spikes, spikes can fall at any arbitrary location of the learning window. And this means sometimes it goes up, for this spike it goes up, and sometimes it goes down. Sometimes the weight goes down, here it goes down. So what really matters is the surface of this STDP window, and this part is counted positive, and this part is counted negative. So the relevant quantity is something like, I take this window, TJF minus TIF. So let's call this difference, the timing difference S. What matters, what drives it upwards or downwards, is the integral W of S ds, which corresponds to the positive surface minus the negative surface. Okay, now you see that if I have more presynaptic spikes, then for each spike, for each postsynaptic spike, there are many contributions. So what matters is how many spikes I do have per postsynaptic spike. So if I consider now all pairs of different spikes, it's clear that the number of pair, here's a postsynaptic, here I have one pair of pre-post, here I have another pair of pre-post, here I have a pair of post-pre, here I have another pair of post-pre. Same thing over here, a pair post-pre, a pair post-pre, a pair pre-post. That the number of these pairs increases with the presynaptic spike arrival rate. If I consider a certain time window over which I count the rate change, and I consider all pairs, then I see that the number of pairs will increase also with the number of postsynaptic spikes. If I have more postsynaptic spikes, then I have even more of these pairs. So the change, the total change in a window of time length capital T will be proportional to the rate of presynaptic spikes and the rate of postsynaptic spikes, and this integral over the window, the surface under the window. And then if I increase T, then overall I will have more and more spikes, so there should be another factor, capital T. So as a final step, what we can do is to consider the change per time interval T. And so I can consider delta Wij divided by big T, and then you see that the big T has moved from the right-hand side to the left-hand side, and I have just this expression here. Now this allows me to answer my question. I asked, what is the relation between spike-based plasticity and rate-based plasticity? So what we found is that in spike-based plasticity, I have a weight change divided by the total interval over which I consider the weight change. And this weight change is proportional to the presynaptic rate, proportional to the postsynaptic rate, and proportional to a constant, and this constant is just the integral over the learning window. The other terms don't play a role at this stage of the argument. So our intuitive approach yields a relation from SDDP to rate-based models, and you see immediately that this is a standard Heppian learning model. I will continue with the argument, but in a more mathematical setting using independent Poisson processes, and those who are not interested in the mathematical details may just skip the mathematical details and go directly to part 7.